Good afternoon, everybody. Hope you all had good weekends. Welcome to lecture on this Monday. So we're going to start off with a survey here, our survey that was opened at the end of the last lecture, and now we're going to talk about it. This one has to do with resonance structures of a molecule called nitromethane. So nitromethane is used as a top fuel for like drag racers and things. It really allows them to go really fast because they can put a lot of fuel in. It doesn't require nearly as much oxygen to combust cleanly. So vehicles that need a lot of horsepower right away can dump a lot of fuel in and don't need as much oxygen, so they can get way more power than they would otherwise get. But anyway, it's a molecule that has a Lewis structure that I'm showing here. This is one Lewis structure for it, and you can see carbon has 4 bonds, it has an octet. The nitrogen here has 4 bonds and it has an octet. All the atoms actually have octets, oxygen as well. And then there's some formal charges. Oxygen here has a formal charge, nitrogen there has a formal plus charge. And the question wants you to know which of the following molecules is a valid resonance structure of that molecule. And so resonance structures are just different arrangements of electrons, no changes in the atom positions, and also you can't add or delete any electrons, and so you really just can move them around. And the way to think about this is if you started an arrow where the electron density is most rich, so on this negatively charged oxygen, and you tried to push it such that you share the electrons differently with another atom that maybe would like extra electron density, take a pair of electrons off this oxygen, push them in to form a new nitrogen-oxygen double bond here, and then take one of the electron pairs out of this nitrogen-oxygen double bond and give them to the top oxygen. So really what this is the 2 oxygens shown sharing the negative charge. And that would give you resonance structure B, as is shown here. And all of the others have something wrong with them. Structure A, it might look good initially because the electrons are shared really evenly, but it violates the octet rule on nitrogen in a way that can't happen. So nitrogen, since it's a small element in group 2, or row 2, I should say, it really isn't able to form more than 4 bonds. So this is an error drawing to nitrogen. So 5 bonds to nitrogen is incorrect. This is not a correct resonance structure because it's got too many electrons. It has 2 negative charges, so it's a different molecule. And structure D, it has a different arrangement of atoms. So the hydrogen is on an oxygen here, whereas that carbon is lacking 3 hydrogens, and so it's a different molecule. Can't be a resonance structure. So B is the only one that works here. That's the one that's the correct answer. And if you select B and hit, and then there's like, what's the confidence that I have in my answer? And I'm going to hit strong. I'll submit this quiz. What you get for feedback is there's an explanation that tells you what the right answer is. So the right answer is B. And that's what is being indicated here. When I scroll down, there's a good explanation of this that I put in. Usually I try to put in pretty detailed explanations for why a particular answer is right, maybe why some answers are wrong. Too many bonds to nitrogen, too many valence electrons, atoms connected differently, all things that are a problem for resonance structures. And then this is the correct one. Okay, when I look at the statistics of this, what you get is a different picture than what I see. I get this screen that shows me the distribution of answers. So I can see that almost everybody selected B, which was the correct answer. There's a check mark next to A, but it doesn't mean anything. It doesn't mean that was the right answer. It's just that these ungraded surveys don't really have a correct answer that Canvas recognizes. So for whatever reason, it just puts a check mark next to A. So I was happy to see 75% of the class got this one right. And then the confidence was pretty high. I mean, it wasn't overwhelmingly high, but it was quite high, so that's good. It's not an easy concept, resonance structures. It's one of the things that a lot of times gives students trouble. So we'll have to practice it as we go along, but it can help explain a lot of things in organic chemistry. So we're gonna try to get good at it and practice it throughout the course. All right, we had an Alex assignment due Sunday night, and that was the homework 0 assignment. If you didn't get a chance to do it because you had problems with getting Alex set up, or maybe your financial aid hasn't come through or whatever, I put in the announcements a way that you can get free access to Alex for 2 weeks. So Alex has this system where you can request what they call a financial code. That is like a 2-week preview of your subscription that you can use while you wait for your financial aid or your whatever your finances to clear. So check out the announcement, and that'll enable you to get started on the Alex homework right away if you haven't been able to so far. And if anybody is didn't get that assignment done because of that, send me a message and I will give you an additional extension beyond the ones that you get 2 free extensions for throughout the course. Did you have a question? Yeah, thanks. Yeah, so this is what I've heard is that the bookstore sells codes for this, but they're out of stock. So they actually sell codes on like a piece of paper, which will definitely work. And we're going to hope they get those in soon. For sure by 2 weeks, it should be no problem. So don't wait for the bookstore to get the codes in. I mean, sign up for Alex right away with the financial aid code and then get to the bookstore when you can, if you have to buy it that way. Some people do for financial aid reasons. They can't just go and buy it online. But if you can buy it online, if you're like paying some other way than like requires you to buy it from the bookstore, get it off the Alex site because it's less expensive and you'll have it immediately. So they have an e-commerce site that'll allow you to purchase right through their site. So when you go to enter the course, there's something like purchase through e-commerce. If anybody has questions about that, let me know and I can help you navigate through that. But definitely like to get everybody access to Alex and working on the homework very soon, because we have another assignment that's due tomorrow night, actually. That's the homework, lecture homework 1, which is for chapter 1, part 1, and deals with all the stuff we talked about last week, basically. Okay, any questions about resonance structures so far? Okay, let's talk about briefly some alternate representative forms of molecules. So we know about Lewis structures now, which are diagrams that show the connectivity of molecules. They show atoms being represented by their code in the periodic table, like carbon is C and nitrogen is N and oxygen is O. Bonds are indicated by lines. 1 line is a single bond, 2 lines is a double, 3 lines is a triple bond. Unshared electrons are dots. But there are other representational forms of molecules that we need to understand and get good with. So there's Lewis structure, first of all. I just put down an example of this. So here's a molecule in Lewis structure form that's showing all the bonds, all the atoms, all the unshared electrons. This is the molecule ethyl alcohol or ethanol. And it's a really detailed representation of a molecule. But sometimes people will draw it in other ways to abbreviate it. Now, it's not really that big of a deal to try to abbreviate ethanol because it's a small molecule. But when you start drawing molecules that are really big and have a lot of atoms, Lewis structures can get a little bit cumbersome, a little awkward to draw big molecules, and especially because all of the detail can sometimes cloud your bigger picture of the molecule. Like it's kind of like not being able to see the forest for the trees if you want to use like an analogy. So there are a couple of ways that people use to represent structures that are more abbreviated and allow you to focus on kind of the core skeleton of the molecule. The first form I'm going to show you isn't quite like that, but it's called a condensed structural formula. And these are ones where atoms are shown with letters, but we leave out the bonds, basically. We usually leave out the bonds. So what people try to do in this case is they'll take the structure like this, and they'll abbreviate it by saying, for carbon, a way to do this in a condensed structural formula would be to say C, and then to indicate that it's got 3 H's attached to it by drawing H and then subscript 3. So that gets the left-hand carbon and its atoms connected. And then the next carbon over will be drawn as a C. And then there's two H's attached to it, so that'll be represented as a H with a subscript 2. And then there's an OH attached to that, and we can represent that with OH. This is a way of drawing molecules as a string of text, basically, just a bunch of characters that run in a row. Really convenient if you're trying to type it into a word processor or search electronically. If you do any work with like chat bots trying to ask them chemistry questions, the output, especially ChatGPT, I've noticed really likes this form because text is like something it can communicate with really, really smoothly. So we're going to get practice in this, learning how to draw these and interpret these in the lab this week. So if you're in the Chem 234 lab, we've got lots of examples of these and how you can take a condensed structural formula and figure out what its Lewis structure is, or Lewis structure to condensed structural formula, basically being able to go back and forth. And they can get a little bit complicated. So I have a video tutorial on this. If you want to watch it, I'm going to link it. It's already linked in the pre-lab assignments for the lab portion of the course. I'll put it in the announcements as well. Really good way to get started with these kinds of representations. The other one we're going to look at are representations called skeletal structures. So these are representations of molecules where there's we're going to leave out the carbon atoms and most of the hydrogen atoms. So I'm just going to draw the structure of ethanol here and in a skeletal structure form, and then we'll talk about it. So that would be how you do it. And what this diagram is trying to tell us is that there is a CH3 at that position, and there's a CH2 at that position. And how you can know that is there's some rules that govern skeletal structures, and they go like this. In skeletal structures, carbons are not drawn in with C. So you won't see like capital C in a skeletal structure to indicate that it's carbon. The way you know a carbon is there is that they occur at the ends of unlabeled lines and it kinks in the structure. Carbons are present at the ends of unlabeled lines and at kinks in the structure. So a lot of times these skeletal structures are drawn as zigzagging type structures, and every place where it zigs or zags, where it changes direction and you get a point like this, that's a carbon. There's also a carbon here, but this is not a carbon because it's not an unlabeled line, it's aligned to an oxygen. So the way you interpret this is that's a carbon, and then this is the OH. So that's carbons, but what about hydrogens? So hydrogens on carbons, on carbon atoms, are not drawn. But are assumed to be present to fill carbon's 4 valencies. Fill carbons, 4 valencies. In other words, carbon needs to have 4 things around it. And if you're knowing where the carbons are, the other atoms are, then you can figure out the rest of the hydrogens just by counting and figuring out how many you need to get to 4. So in other words, this carbon right there is shown bonding to one other carbon. So one of its valencies is obviously to another carbon. We're not seeing anything else, so we have to assume that the other 3 things are hydrogens. That's how you can know it's a CH3. These hydrogens are called implicit hydrogens. They're not drawn in, but you can calculate how many are there. And at first it's going to be awkward, but once you get used to this and thinking about 4 things around carbons, this is a really slick way of looking at molecules because it allows you to appreciate the skeleton of the molecule, the overall structure, and not be distracted by all the hydrogens all the time. That carbon is shown making bonds to 2 different things, a carbon on the left and an oxygen on the right. So it has to have 2 things attached, and those 2 things are 2 implicit hydrogens that aren't shown. All right, and then the other thing is draw in all other atoms like nitrogen, oxygen, sulfur. Any other atom has to be drawn in. The only ones we're abbreviating are carbon and hydrogen. It's because there typically are many, many of those, and it's a good thing to abbreviate. So draw in all other atoms and draw all hydrogens attached to these other atoms. So you're only allowed to delete the hydrogens when they're attached to a carbon. In this case, like with ethanol, there's an oxygen that has a hydrogen. You must show that hydrogen, otherwise the structure becomes ambiguous. That's why I drew an O with an H there. And usually no lone pairs. Usually unshared electrons are left out. Usually lone pairs of electrons are not drawn. And the reason is you don't really need to know the lone pairs to understand the structure. You can calculate that they must be there based on what you see in the rest of the structure and based on the charge state. Lone pairs, drawing lone pairs in skeletal structures is optional. How about handling charge? If you have a Lewis or if you have a skeletal structure, continue my notes about skeletal structures over here. In skeletal structures, comma, a charge takes the place of a hydrogen. Takes the place of a hydrogen, and it fills up one of the valencies on the carbon. So, for example, here's a molecule that has a negatively charged carbon in it. I'll draw the Lewis structure, and then we'll draw the corresponding skeletal structure. So this is a Lewis structure of a 3-carbon molecule, and on the N carbon there's a lone pair and a minus charge. To draw the skeletal structure of this, I draw it like this, and the ends of the unlabeled lines are carbons. The carbon in the middle is the CH2 in the middle, and then on the right side here what I'll do is I'll show a minus charge. So that's the skeletal structure equivalent of the Lewis structure I'm showing here. So the way you can know what's going on is that if you look at this carbon, that's the end of the unlabeled line here, I can see it making a bond to one carbon, that's one valency. Then I see a charge, negative charge, that's the second valency, and then we need to get to 4, so there must be 2 additional hydrogens on here that are implied, that aren't shown but must be there, and that's how you can make sense of this. So it'll take a little practice to get used to these skeletal structures, but they're real common, and we'll see them over and over again, and the homeworks are going to have lots of examples of skeletal structures. Do you have any questions about interpreting skeletal structures for now? Okay, condensed structural formulas will come to, we'll get lots of practice with this in the lab on Thursday this week too. If you're in the lab, you'll benefit from that. So, good. Okay, well, let's talk about some other stuff here that's really important in chapter 1, and that's things that deal with shape. Shapes of molecules, shapes of atoms, geometries. This is the other really big important thing about organic molecules. They have a particular connectivity and they have a particular shape. And both of those things are really important for determining how they behave. So this is a section that's all about determining molecular shape. There is a concept from general chemistry that I'm going to bring back to the forefront of your memory here. Do you remember hearing about VSEPR theory in general chemistry? VSEPR, valence shell electron pair repulsion theory. Let me put that down here. Valence shell electron pair repulsion. Theory, or for short, VSEPR, sometimes referred to as VSEPR theory. Essentially what it says is that groups that are attached to an atom like to stay far apart because electron groups repel each other. That makes sense because if you've got a bunch of electrons around an atom, they're negatively charged, they repel each other. So there's this desire for these groups to stay as far apart as possible. And that's going to lead us to a few shapes that we're going to learn and get comfortable with. So what this theory means or is saying is that electron groups on an atom stay as far apart as possible because the groups repel each other. All right, let's talk about how we can work with this. So I'm going to share with you the 3 shapes that are important in organic chemistry. In general chemistry, you learn 5 shapes, actually. And those we might touch on briefly at some point later on in the course, but the thing about organic chemistry is we're so often dealing with the second row of the periodic table that those atoms don't have 5 shapes available because they don't have d orbitals. So let's talk about some common shapes. So I'm going to make a table for you. So the first column is going to be number of groups. electron groups. And we're going to talk about what an electron group is here in a second. Number of electron groups attached to an atom. That'll be column number 1 in this table. Then I'm going to have hybridization. Which is going to be explained in a lot of detail later, but it's about what orbitals are going to get put together to make that shape. Then we're going to have arrangement of electron groups. We're going to have proximate bond angles. And then we're going to look at some examples. So this big table is going to start with 2, which is the smallest number of electron groups that you have in a molecule. So 2. If you're an atom and you have 2 electron groups attached to you, your hybridization is what we're going to call sp. What that means is the molecule uses an s orbital and a p orbital to build the molecular orbitals that are going to give rise to that shape. We'll talk about that later, but one of the ways you can keep track of this, if you're just trying to latch onto it some way, is there's a 2 here, and if you just count the letters here, there's an S and a P, so that gives you 2. These are going to be linear molecules. The approximate bond angles are going to be 180 degrees, and the reason I say approximate is because depending on the molecule and exactly what the electron groups are, sometimes you can have little deviations from the numbers I'm going to put down here, but in a linear molecule, 180 is what you're going to see. And as an example, the example I can share with you that will hopefully help you understand this shape is this molecule. This is the molecule acetylene. So acetylene is a gas that gets used for welding a lot of times. The carbons in the molecule are the things we're talking about here. So each carbon in this molecule has 2 electron groups. What gets people sometimes is they'll look at a triple bond and be not sure how to count it, but triple bonds, double bonds, single bonds, every atom it's bonded to counts as 1 electron group, and it doesn't matter how many bonds it's making. So in other words, this carbon right over here has a hydrogen on the left, that's 1 electron group, and a carbon on the right, that's 2 electron groups. This carbon is the same way, it has 2 electron groups. So each of these carbons is sp hybridized. And I will put a little sp next to each of these carbons to indicate that's a way we can classify them. The molecule is linear. In other words, it forms like a perfect line down the middle of it. And the bond angles here, like from here to here, that's 180 degrees. And that bond angle there is also 180 degrees. And if you wanted to see what this looks like using a model kit, what you could do is you could get your model kit out and make sure you're using atoms, carbon atoms that have 4 holes in them. The model kits have some atoms, depending on which one you have. Many of the model kits have atoms that have 5 holes. We'll talk about what those are good for later, but if you grab one that's got 4 holes and then you use 3 bent bonds to connect the 2 carbons and then hydrogens, you get this picture of acetylene, and this is geometrically what it looks like. It's a linear molecule. If you look down it, you can look down the bonds or look down the hydrogens, and they're all in a row. Hydrogen, carbon, carbon, hydrogen. And you can do this, rotate it like this, and it's basically, they're all in a line. It's linear. 180-degree bond angles. That's acetylene. The other option is, well, maybe you got 3 electron groups attached to you. Then, if you're an atom in that situation, you'd be sp2 hybridized. And again, you can kind of just count. If you're wondering 3 electron groups, what's my hybridization? One s and 2 p's, that gives you 3 sp2. This geometry is trigonal planar. What trigonal planar is like a 3-pronged propeller, basically. So if you can imagine that, that will really help you like figure out what these things look like. They have bond angles of 120 degrees. If the electron groups are all the same, then it's a perfect 120 degrees. If the electron groups are a little different, the bond angles might be distorted a little bit from 120, but overall, the 120 is about where it's at. And as an example of this kind of a molecule, I will show you a carbon-carbon double bond. So in this structure, we've got each carbon having 3 electron groups. Carbon on the left has a hydrogen, and a carbon. So that counts as 3. Doesn't matter that it's a double bond. Each atom counts as a group. So this is an sp2 carbon atom. This is an sp2 carbon atom. And the bond angles between the groups are 120 degrees, about 120. So that's that molecule. And if you wanted to build a model of this to see what it looks like, you could do the same thing where you grab a carbon that's got 4 holes, and into those holes plug in 2 bent bonds between the carbons, and then 2 hydrogens. I'm representing the hydrogens with really short bonds because that's the way hydrogen makes bonds. Hydrogen-carbon bonds are really short. But here's our trigonal planar molecule. The carbon here kind of looks like a 3-pronged propeller. It's a little lopsided because this electron group isn't the same as these, but it's a 120-degree bond angle between the bonds, and it's trigonal planar that way, and you can turn it this way, and it almost looks flat, like I could lay it on the table. So that's an example of sp2 hybridized atoms. And then the last type of shape that we're going to have to worry about is if you've got 4 electron groups attached, and atoms that are like that, they are sp3 hybridized. They have a tetrahedral arrangement of groups. And they have bond angles of 109.5 degrees. And as an example, I'm going to show you ethane. That's carbon bond with hydrogens attached. Now here's the thing, tetrahedral atoms aren't super easy to draw on a 2-dimensional surface. We have to have sort of a trick to enable us to do that. And so the way that people draw a tetrahedral atom is they'll use dashes and wedges. So as an example here, the carbon I'm drawing on the right side has bonds that are shown as lines. Those are ones that are sitting in the plane of the board. And then on that carbon, there's a wedge bond, and you can imagine that one is one that's poking out towards the board, closer in space to your eyeball. Then there's one on a dash bond. That's one you can imagine is further away from your eye, so it's like behind the board. And each of these carbons has one of each, a dash and a wedge. So we do this to represent the structure of this 3-dimensional molecule, because a tetrahedral molecule is kind of like a tripod. And here's an example of the ethane molecule. So I've got my hands here on the hydrogens and the bonds that are in the plane of the board. And then if you look, I'm just going to grab here, this one and this one are closer in space to your eye. These are closer to you. So they appear to try to indicate that with the picture. We show this bond getting bigger as though we're getting bigger because it's closer to your eye. So from a perspective, from a 3D perspective, these hydrogens are closer, they're just a little bigger. And the bonds get bigger as they get closer. The ones that are on dash bonds are these right here. They're further away from your eye. And those are ones we're showing on dash bonds because that's one way to indicate that they're further away. So we'll get good at this as we move along. But what you'll notice is it's not a flat molecule, and you can never make it flat. And you can rotate about the bonds, but it's never gonna be flat. So if you drew a Lewis structure of that molecule, you might end up with something that looks flat, but the molecule's true structure is not flat. Each carbon atom is tetrahedral. All right, so let's talk about drawing a tetrahedral atom and just some pointers, some tips, things like that to help you get used to it or start to get comfortable with it. And this will be useful when you start doing drawings in ALEKS as well, because there are some rules about how you draw tetrahedral atoms that matter both on ALEKS and both on exams and things, so that you're not drawing a structure that's like physically impossible. So how to draw tetrahedral atoms. So we'll take methane as an example because it's really an easy one. It's the simplest one I can think of. So I'm going to take this ethane molecule and I'm going to make it into a methane molecule. So here it is. If you sat it down on the bench in front of you, it looks like a tripod. So the way we represent that is we pick two bonds to lay in the plane of the board or the plane of the paper or the plane of the computer screen, and we draw those as lines. So what I'm going to do with this representation is these bonds that I have my fingers on right here, these are the ones I'm going to choose to show in the plane. And then this one is going to be closer to your eye, so that one's on a wedge, and this one's further away from your eye, so that one's on a dash. So I'll just set this down, and then we'll go do this. So I've got a carbon, and I've got on my carbon, I've got a hydrogen that's going straight up, and then I've got one, it's going down and to the left, and those are my in-plane bonds. And then on the left side over here, that's where I have the wedge and the dash. And it doesn't matter whether you show the dash and the wedge like I'm drawing here, or I'll show you the alternative. They mean the same thing. So there's one representation of it. Another way to draw this that would be exactly the same would be like this. I'm just switching the position of the dash and the wedge, but I'm not changing the molecule. And the reason that works is because these are what are called perspective drawings. And the way that you view these things is when you view them, the front atom is actually exactly right in front of the back atom, and it wouldn't be possible to see. So what we do is we tip it just a little bit. You tip it a little bit, and then you can see the one in the back. If you had this rotate a little differently, the front one would completely obscure the back one, and then it'd be confusing to look at. So the way this is drawn is a perspective where these are in the plane, and then these are tipped just slightly, either slightly like this or slightly like that, but it means the same thing. The big things and these things can be rotated in all sorts of different directions too. So I chose to pick this one and this bond to hold in the plane, but you could choose any plane, you could choose any bonds to hold to the plane. I could have drawn it like this, for example. This is just a different rotational form of the same molecule. So one of the things we're going to learn in lab this week is that molecules, when you rotate them, that doesn't make them different. If you just simply rotate them as a whole, they're the same. Even rotating about bonds doesn't change a molecule. Single bond rotations don't change it either. So these are all equivalent, correct ways of drawing methane, and there's all kinds of others too. I could have flipped this one upside down. I could turn it 180 degrees. They're all the same. The things you don't want to do though, you don't want to do this. Don't show bonds like this and then show anything in here. Like this is not a correct way to draw. So this one is bad. I'm going to put a big red line through it because when you look at the molecule, its perspective doesn't look like this. This wedge is in the wrong spot. The wedge needs to be over close to the dash. The dash and the wedge need to be close together, and they need to be in the wide space between the two lines. So the two lines should be about 109 degrees angle apart, and then in the bigger angle, that's where you show your dash and your wedge kind of close together, like that. We'll get lots of practice with this, but lab this week is the first place you'll draw a bunch of these. So, any questions about these representational forms? All right. Well, let's talk about hybridization and bonding then. So what is it about these letters that are giving these shapes? SP, SP2, SP3, what does that even mean? It has to do with the atomic orbitals that go together to make the different shapes. So I think what I'm going to do is just try to maybe leave this up for a little while so we can appreciate it. So hybridization, I'll give you like a non-chemistry example to get you started with the concept. Lots of things can hybridize. If you take two objects and you mix them together, you can get something that looks a little bit like each one of the originals. Trying to think of a animal example of this. When you cross is it a horse with a mule, you get a donkey, something like that. Is that you cross it? Okay, say that again. Cross a horse with a donkey. Okay, you cross a donkey. Yeah. Okay, so that's so you get something that kind of looks like each one of the parents, but isn't quite the same. So it works the same way with objects, and that's what an atom is. So hybridization. Let's do a non-chemistry example. So imagine you had a spoon. And you mixed that with a fork. And you were to hybridize these two objects. You mix them together and you get something out that's kind of like the sum of each one of the individuals. You get anybody ever eaten with one of those before? It's a spork, yeah. So it's a little bit like a spoon and a little bit like a fork. And actually, following the rules of combining orbitals, you'd get two sporks. If you mix one spoon and one fork, you get two sporks. Orbitals are kind of like that. And with these hybridization types, what we're doing is we're mixing an s with one p, or mixing an s with two p orbitals, or we're mixing an s orbital with three p orbitals, and we're going to get these different shapes as a result of those hybridizations and mixings. So what I'm going to do is draw you these three different pictures of the three different hybridization types and explain how bonding works with those. So the first one we'll tackle will be sp hybridization. Well, actually, let's do sp3 because it's maybe a little bit more intuitive because we're mixing all of them together. So sp3 hybridization. So what we're going to do is we're going to take 2px, 2py, 2pz orbital, and a 2s orbital, and we're going to mix them all together. And we're going to get out some hybrid orbitals. And the rule of mixing orbitals is that if you start with 4 orbitals and you hybridize them, you got to get 4 orbitals out. And so what comes out of this is, that's the nucleus. I'm going to show the hybrid orbitals in blue. So there's like 120 or 109.5 degree bond angle here. Then there's an orbital here, and then there's an orbital like there that's kind of hidden, partially hidden behind it. So this is a tripod type shape. These are all hybrid orbitals. This is an sp3 orbital. This is an sp3 orbital, sp3, sp3. That's mostly what they look like. They have additionally, and if you see this in the book, you'll see it, in addition to these big lobes, each one of the big lobes has a really tiny small lobe that fits behind it that is kind of hard to see, but we'll talk more about those when we get to chapter 7 as to why those are important. But when you look at it, this is what they look like. They have one big sort of oblong lobe, and these lobes are what electrons go into to make bonds with other atoms. So when we look at a like molecular orbital picture of this, these are hybrid atomic orbitals. Molecular orbitals are what you get when you overlap these atomic orbitals. So like methane, for example, a methane molecule looks like this. It's got the center carbon. So carbon would be at the center of this. And if it's sp3 hybridized, it's got an sp3 hybrid orbital here, sp3 hybrid orbital here, and then it's got that front orbital there that's sp3, and the orbital that's kind of being obscured by it a little bit in the back there. And then if you bring 4 hydrogens in to make bonds with this, the hydrogens are going to be next to it, and they have a s orbital. So hydrogen has 2s. A 2s orbital, that's all it has. It can't form any hybrid orbitals because it only has 1. So when you get a bond between a carbon with an sp3 orbital and a hydrogen with an s orbital, they're going to share electrons in the space of the overlapping orbitals. And then a hydrogen up here, an s orbital, and the overlap is where the bonding happens. And then here, got a hydrogen there and a hydrogen here. And so what this is trying to show is what a methane molecule looks like that has this structure. 2 of the bonds are in the plane, and then there's a wedge bond to a hydrogen here, and a dash bond to a hydrogen there. So this is the structural picture that we draw with dashes and wedges. This is what a molecular orbital diagram looks like. It's got hybrid orbitals, and I know carbon in this situation is sp3 hybridized because it's got 4 electron groups, 4 hydrogens around it. But this is what the orbitals are doing. This is why actually bonds happen, is because the orbitals overlap and then electrons are shared in the overlapping space. All right, well, let's tackle sp2 then. So sp2 is one that mixes some of the orbitals, but not all. Hybridization, sp2 hybridization. So what this looks like is you get, and I think what I'm going to do is just say, without specifying px, py, or pz, I'm just going to say we're going to mix three of these orbitals. We're going to leave one out. So atoms will sometimes do this. They'll take the 2s and 2 of the p orbitals, mix them together, and get a new shape that looks like this. There'll be a nucleus in the middle, and I'll draw the hybrid orbitals in blue. sp2 orbital, sp2, sp2. So we mixed these three orbitals together, and we got three new hybrid orbitals, which are shown here in blue. And this is where the three-pronged propeller shape comes from. So this is like a propeller shown edgewise. If you turned it like this, you'd see the prongs of the propeller with 120-degree bond angles. So that is the hybrid orbitals, but we've got one leftover p orbital that we have not accounted for, and that's actually right here. Let me see if I can. My green is a little weak here, but I'll see if I can highlight it a little better. This is a p orbital. There's a p. It's one p orbital. There are two lobes. Each p orbital has two lobes. These are the two lobes of the one remaining p orbital that did not get hybridized. So that's what that looks like. And when you have a molecule that's making bonds like this, I'm going to show a carbon bond, sp2, and then next to it I'm going to draw another carbon, and I'm going to show its sp2 orbital happening here. So this is a bond between the two carbons where there's two overlapping sp2 orbitals. sp2, sp2, and then this one similarly has sp2, sp2. So these are two sp2 hybridized carbons that are bonded together like this. And then they each have an unhybridized p orbital that is left over. P, 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 P. And these p orbitals overlap too. So there is some bonding that happens between the p orbitals. So there's two bonds actually between these two carbons, two different kinds of bonds. This bond between the hybrid orbitals, this is called a sigma bond. This overlap between the p orbitals, this is 1/2 of a pi bond. And this overlap up here is also, that's the other half of a pi bond. So this gets us into a couple of different kinds of bonding. So sigma bonds are when you have direct sharing of electrons between atoms, like these two overlapping sp2 orbitals, two electrons shared in this space, that's a sigma bond. All single bonds are sigma bonds. When you have a double bond, like we're seeing here, one of the bonds is a sigma bond and the other one is a pi bond. And then I'll draw in hydrogens here as being attached to the ends of this molecule. And each of the hydrogens is bonding via its s orbital. So this is a molecular orbital picture that's trying to tell us what a carbon-carbon double bond really looks like. So this is a carbon-carbon double bond that's shown on its edge, where the hydrogens function as 2 electron groups on that carbon, and the other carbon is the third electron group. So that's why it looks the way that it does. Then we got one more to deal with here, and that's the sp hybridization. So sp hybridization. This is what happens when an atom mixes just 2 orbitals, takes these 2, mixes them together, and you get a molecule that, or you get a shape that looks like this. So there's a nucleus, and you get 2 sp orbitals that are exactly opposite each other. And so this is what gives rise to 180-degree bond angles. But then there are these 2 p orbitals that are left over. And so one of the p orbitals I'm going to show as being up and down. And then the other p orbital juts out of the plane of the board towards you and into the plane of the board behind you. So these are the 2 unhybridized p orbitals that are present on an atom that has sp hybridization. And so a model of this for a molecule that would look like this, I'm going to draw a couple of carbons here that are making sigma bonds between sp hybrid orbitals. Their other sp hybrid orbital points 180 degrees away, and I'll show that bonded to a hydrogen in each case through the hydrogen's s orbital. So these are all the sigma bonds in the molecule, but then each one of these carbons has an unhybridized p orbital, and there's a couple of them that go straight up and down, p, 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 p. So you get 1 pi bond right there. And that's half of it, and that's half of it. And then there's another unhybridized p orbital on each one of the carbons that juts out and into the plane. And there's overlap between these p orbitals as well. So that overlap looks like this. So this is a molecule that's got 1 sigma bond between the carbons, and then 2 pi bonds. And this is the structure of acetylene, that linear molecule I told you about at the very start of the lecture. It's a triple bond, but the 3 bonds aren't exactly identical. There's 1 sigma bond and 2 pi bonds that make up the triple bond. And that's how you get a triple bond. It's some of the electrons sharing directly between carbons, and then others sharing in the space above and below the plane. The reason is you can't get more than 2 electrons between the 2 carbons because they won't fit. They start to repel each other, so each of these orbitals can only hold 2. So that's a discussion of hybridization and bonding. We will continue with chapter 1 for just a little bit. When we come back on Wednesday, we'll talk about electronegativity some more, and we'll talk about polarity. And then we'll move on and we'll start talking about acids and bases in chapter 2. So see you on Wednesday.